Hello friends. Today we will continue our physics journey and talk about sources of forces. Alright, so we're going to talk about what can exert forces. And we're going to talk about a whole host of things, including gravity, springs, ropes, normal force, and friction, which is basically everything you're going to encounter in a physics problem, especially in, they call these units like statics and dynamics, where you're going to be working with objects or systems that are either not moving or moving. But we'll get into that. Let's dig in. So before diving into our questions for today, we should talk a little bit more about force. All right, force is a vector. That means it has magnitude and direction. But the way you express forces in physics is you make a force body diagram or a free body diagram. And you can see on this slide, you can see a box it has the force of gravity pointing down and the force normal pointing up. We're going to talk more about those later in the video. But just some things to take note of. For now, since we're thinking just about like linear motion, we're going to be thinking that all force is acting on the center of mass. So we're treating all objects as point masses, right? Like this water bottle is not a point, but really you can think about it as having a center of mass that you can treat as a point mass. And then that means if I can push this water bottle, and if it's it's like at the center of mass, then it'll just move like that. But in real life, if I move it like this, you'll also be applying like a rotational equivalent of force known as torque. And we'll get into that in later videos. But that complicates things, and that makes a whole host of problems like slip tip problems, which are all fun and good. Yeah, and a good thing to know is that when all forces are balanced, meaning like they all cancel each other out, F equals ma, F is 0, that means you're in static equilibrium, which means that you're not accelerating. And that makes sense. If you look at F equals ma, 0 equals ma, then a must be 0 because, in order to have an object, you must have mass. So yeah, static equilibrium, no acceleration. Our first question is, what can exert force? And the answer is a lot of things, right? And I'd like to think of like two classes of force. One is contact forces. So it's things you usually see in your everyday life. Like I can exert force, living things can exert forces, and then, machines or simple machines like springs and ropes and friction. Friction's fun. But then there are these four universal forces, which means they don't require like this idea of touching. They're forces at a distance. And you only really need to know gravity in our case, because the other two, they're more complicated. You get into them later in physics because they ultimately just require a lot more like mathematical understanding and just deeper understanding of physics in general. But yeah, there's the strong and weak forces, which govern the nucleus and like the actual atoms themselves. There's electric and magnetic forces, which govern charges and electrons, and those are super interesting. I hope we get to them at some point in this series. And then gravity governs masses. So all masses can exert forces on each other from a distance, and that's crazy important. And that leads us into our second question. How does gravity work? Well, basically any two masses at a distance from each other will exert gravity on each other. By Newton's law of gravitation, F equals gmm over r squared. And note that g is 6.67 times 10 to the negative 11th meters cubed over kilogram second squared. Just know that like those units right there are kind of turning the units back into kilogram meters per second squared, which is newtons, which is force. But the main idea here is that like masses need to be huge for gravity to actually like make a difference, because that g constant is so small. And yeah, if you look at the equation m1, m2, it's pretty self-explanatory. Those are the two different masses. G is the gravitational constant. R is not the radius. R is the distance between the center of masses of the two objects. So usually you'll be thinking about this sort of gravitational concept when you're thinking about planets, right? Earth is obviously exerting gravity on us. The moon and Earth is exerting gravity on the moon, but you also have to realize that the moon is exerting gravity on Earth. So Newton's third law applies here, and I think that's a really important thing to know. So like when I jump up in the air, Earth is pulling me down, but I'm also pulling Earth up a little. The reason that it seems like the Earth is pulling you down is because, think about it, F equals ma. You both are exerting equal forces on each other, but you're a much smaller mass, so you're going to accelerate much more than the Earth will. The Earth will only accelerate a tiny bit because its mass is gigantic, but the force is constant. And that's basically just how gravity works. Next question is, what is a gravitational field? And this is also a pretty important concept, but it makes sense. It's a method of expressing gravity that the gravity an object exerts over space. So the further away from an object you get, like there's less gravity. And if you look at the picture on our slide, it can be expressed as like concentric circles, or if you're thinking in 3-dimension, concentric spheres, where like each circle, since it's equidistant, that means it's also equigravitational. And on the surface of the Earth, that means like you basically are always in the same plane. Like a change in distance is not going to matter that much, because the Earth's radius is so big that it's just like it's a tiny little nudge in the force of gravity. So that means if you look at our equation, F equals gmm over r squared, where one of the m's is Earth, like 3 of the things on the right hand of the equation are constant, are basically constant. G, the mass of the Earth, and the distance of the Earth, if we make that approximation. And that actually gives us an important result, because when you put those things together, you get F equals 9.81, so it's always going to be constant. It's going to be this number times m. All right, hopefully the dog issue was resolved. But F equals 9.81 times m. 9.81 is always constant. And if you look at this, you realize that this equation, oh God, this dog really doesn't like me. This constant is actually acting as the acceleration in this equation. I mean, you could prove that with using all like the different, units and stuff. But you can see F equals ma here, where 9.81 is acting as the a. And this is sort of an important result. So when you're in a certain like level of the gravitational field, you say that the force of gravity is going to just be constant. It's not going to be, you're not going to be worrying about distance. So it's going to be F equals mg, where g is your gravitational is the gravitational constant. And on the surface of the Earth, that is 9.81 or something around that, but usually 9.81. And this g value is called your acceleration due to gravity. And that is constant when you're in a certain area. So okay, that's the gravitational field. Now let's talk about springs. Okay, springs, you know sort of what a spring is if you've ever worked with like a slinky, or you've seen sort of springs like when you're putting batteries in. Springs are objects that can be deformed, so you can like push them in or let them come out. You can pull them out, but they'll return to their original shape within like a certain, radius of reasonability. If you pull it too hard, it'll break, but we'll talk about that more later. So basically the force that a spring exerts, it depends on the distance that you pull it, right? And that's expressed in a law known as Hooke's law, which says that the force of a spring is equal to negative kx, where k denotes the sort of elasticity, the stiffness actually of the spring. So the more stiff a spring is, the more that sort of resistant force is going to come back at you. And the reason it's negative is because this force is opposite to the sort of direction of displacement. So if I'm pulling it away, the force is going to be acting inwards towards the like equilibrium position of the spring, which is just like its natural position. So F equals negative kx. That'll be very important. But I want to dive a little deeper into springs, because I feel like most classes don't, at least in like the beginning aspect. So I put here a stress versus strain graph, which every sort of material has this. So first of all, what is stress and what is strain? Stress is the force per unit area in an object, technically, but I mean, I just like to think about it as the internal force that this object is sort of exerting back on me. And then the strain is its deformity, so it's actually the change in length over the original length. So what this is saying is that in this initial part of the graph, you have this sort of area of elasticity where your stress and your strain have a linear relationship. So as I pull on something, it's gonna have an internal force that's directly proportional to that. And in this area, Hooke's law is obeyed. And springs happen to have an area in this curve that's like very usable. It's pretty long, so you can so it actually becomes useful in a problem. Usually most materials like don't have a very big elastic sort of range. If I pull this water bottle, it'll just sort of immediately, or not immediately, but almost immediately just break. But yeah, the slope on this graph of this, like the linear part of the stress versus strain, that is called Young's modulus, and it actually, for springs, it's directly proportional to your K, which is your stiffness. But Young's modulus is just like a more general term. So then, okay, now we're gonna talk about ropes. How do ropes work? So ropes, you're familiar with ropes as well, but in physics problems, you usually make some assumptions about ropes. The first one being that the rope is gonna be massless. And the reason that's an important assumption is because then you could say that you can make this assumption known as same rope, same tension. So throughout the entire rope, you're going to have the same internal force. So like if I'm playing tug of war, that side of the rope is going to be pulling with the same force that my side of the rope is pulling. So really, if I have, hi Holden. So if I have like this string, right, the tension here is going to be constant throughout it, if I assume it's massless. But in reality, if you're actually holding a string, this part of the string is going to have to hold more than this part of the string, right? Because they're on different ends of it, and gravity's going down here. And that's sort of a consideration you have to make when you're working with heavy ropes. But usually, you can just make the assumption, same rope, same tension, massless rope. And you also assume they're not elastic, so you're not sort of working under the same sort of material science I was talking about earlier with the stress versus strain graphs. Like when you're just going to pull it, and it'll have a tension force, and it'll have a breaking point, right? The rope, if I pull this hard enough, this string will break. And obviously, a rope will always pull, right? I exert a certain like tension on it, or if I pull it hard enough, it'll have a tension, right? And this, but if I don't pull on it, it's not gonna. You can't push something with a string. It just doesn't work. It doesn't make sense really, and even intuitively. Next question: how does normal force work? We talked a little bit about normal force in the last video, but it's something that just comes up a lot. So I want to really get that down because it's sort of a confusing concept. So the way we talked about it last time was in the context of Newton's third law. So we talked about it as a reaction force, where it's perpendicular to the surface of where it's acting on. So the frictional force, and the normal force is going upwards on my hand that's pushing this hand down. But my physics teacher told us something really interesting. It's sort of a good way to think about it is normal force is a measure of squeeze, right? So a scale is a normal force indicator. Oh God, the dog. A scale is a normal force indicator. So if I'm standing on a scale, it's really measuring the force that's going up. Like if you look at the presentation, like you can see this object, right? And let's say it weighs 100 newtons. But I can attach a string to the top of it, and if I pull it a little bit, I can actually reduce that weight because I'm doing a little work for it. Like normal force is so there's that gravitational force that's going down, but then there's normal force as well as the string force that I'm pulling it up with. And normal force will adapt to that. It's not going to stay the same and make it go up suddenly. That wouldn't really make sense. It's a reactive force. It's smart. So different circumstances will require different normal forces. Therefore, you shouldn't just walk into a free body diagram into a problem and just immediately draw your normal force and assume what it is, because usually it's going to be smart. It's going to change. And you'll see that in problems. Next question, how does friction work? So let's just think about something. If I have my two hands right here, if I push them together harder, right, then sliding them is going to be more difficult than if I just like keep them here and just try to slide them this way. So obviously squeeze is going to be an important part of normal force. Of friction. Sorry, I just gave it away. Friction is dependent on the normal force, as well as, well, if I like greased my hands up, then this would also be easier. And that's something that just depends on the material. So that other sort of part of friction is called the coefficient of friction, and it's dependent on both parts, both objects, right? So steel will have a different coefficient of friction against glass than it would against other pieces of steel or stone or whatever. So yes, friction, the general term for friction is force of friction equals mu, which is your coefficient of friction between two objects, and your normal force, your squeeze between them. And there are two types of friction, really. There's static friction and there's kinetic friction. But first let's look at this graph on the slide. So we see that when we're applying a force on an object, right? If I have this water bottle and I'm applying force to it, I'm going to keep the frictional force is going to balance out the force I'm pushing until I reach a certain point, and then it's going to start sliding. And the reality is the sliding sort of friction is less than the ultimate static friction. And the reason that is I kind of drew out like a little messy thing on the slides, but it's like when you have two things that are like against each other and not moving, their grooves sort of like match with each other. And they sort of fill each other. And I know that's a weird way to think about it, but it really does happen on like an atomic or a molecular level. But the thing is, when you start moving, then it's not going to be like falling into like it's like little nooks and crannies as it would before, so that it has an easier time sliding over it. And you can see on that diagram, it sort of kind of goes up a little bit, so it's easier once you get it rolling. So that means in most problems, though, you're going to be kinetic friction will always, change based on like as you're moving, how fast you're moving and stuff. But we're going to assume it's constant when you're moving on an object usually. And then static friction will also be its own value. So things to take away from this: static friction is bigger than kinetic friction. And in a problem, well, they're just going to be different. And kinetic friction will apply when you're pushing an object or when an object is moving. But static friction, it's sort of, when you have the static friction like coefficient, that's telling you like, that's like the maximum. So the force of friction max equals the static friction times the normal force. So the normal force can change, but just know that like static friction is there in reserve. It's waiting to stop you, and there's a certain amount of it, okay? And you can use up all that static friction, and then you'll just switch to kinetic friction, and it'll have an easier time sliding. So there. And I wanted to include this diagram. This is an inclined plane, which is a common problem or a common sort of thing in physics classes, so I thought I should touch on it. So it's a box on an inclined plane, which is like it's a plane, but it's inclined. So yeah, you're going to have your force of gravity pointing down. You're going to have a normal force, which is normal to the surface, so it's pointing outwards. And then, so you can also see, force of gravity is mg, like we talked about. In a gravitational field, we're going to assume constant gravity, so then mg. And the thing is, using trigonometry, you can split this up into mg cosine theta, which is sort of perpendicular to the incline, and then mg sine theta, which is parallel to the incline. And you're going to have friction right there, which is balancing out the mg sine theta if your mass is, if there's enough friction, obviously. I mean, it depends. Sometimes it'll be moving. But assuming this is in static friction, then the friction will balance out the weight parallel, and the normal force will balance out the weight perpendicular. And you can change this problem up a lot. You can add ropes and stuff, make it all the more tricky as you wish. And that is all the questions we have covered today. And I just want to give you some advice. So I've talked a lot about all these different, forces and things, but really, if you want to get better at physics, you have to do two things, in my opinion. The way I learn, it's one, you have to do more problems. So I'm going to put more problems in the in my link in the bio, so you can read those, and diversify your sources. So don't just use me. Don't just use Khan Academy. Don't just use one textbook. I think the best way to learn really is to just go through all of them, and sort of see how different people explain it, and then you just get a better sense. So yeah, do problems, diversify your sources. Thank you, and stay healthy.